Hello, everybody, and welcome back to another Geography 340 Climatology lecture. I am Dr. Zach Hilgendorf, and today in this lecture, we're going to be talking about the global energy budget. So, some definitions to remember. First off, we've got greenhouse gases. So these are gases in the atmosphere that absorb infrared long-wave radiation emitted by the Earth. Now, if you remember in our last video, we talked about kind of the ways that radiation are absorbed, and we were thinking about insolation, so incoming solar radiation. These are long wave radiation that's emitted by the Earth that are absorbed by gases in the atmosphere. Then we've got the greenhouse effect. So this is the transmission of shortwave radiation by the atmosphere coupled with the selective absorption of longer wavelength terrestrial radiation, especially by water vapor and carbon dioxide, resulting in the warming of the atmosphere. Now, we're going to talk about the greenhouse effect a little bit more later on. But that's not to say that the greenhouse effect is bad. Actually, if we didn't have the greenhouse effect, we wouldn't be able to live. We would have an uninhabitable planet. But the issue of anthropogenic climate change and greenhouse gases is where that kind of comes into play. So we'll talk about that a little bit more in future videos. We've got convection. So this is the transfer of heat by the momentum or by the movement of a mass or substance. This is only pertinent to fluids, so air and water. Conduction, the transfer of heat through matter by molecular activity, also transferred through molecular collision. And then condensation, the change of state from a gas to a liquid. Evaporation, the process by which a liquid is transformed into a gas. Latent heat, which is the energy absorbed or released during a change of state. And then sensible heat, so that's the heat that we can feel or measure with a thermometer. So let's look here and just think back, long ago maybe to our phase changes of water. So we go for water, we go from solid to a liquid and vice versa. Solid to a liquid, we're melting, freezing if we're going from a liquid to a solid. We've got evaporation if we're going from a liquid to a gas, or condensation if we're going from a gas to a liquid. We've got deposition if we're going from a gas to a solid. So think of deposition, things like frost, for example. Frost forming on a blade of grass or a leaf or on your window. So that would be a form of deposition. And we've got sublimation, which is a solid going directly to a gas. So the red arrows are indicating heat energy that is being absorbed from the environment. So where these molecules are being excited, there's more energy in the system. And then the blue heat energy is released to the environment. There is a loss or a decrease in energy moving from a gas to a solid. Those molecules are slowing down, right? So if we think about how energy is distributed across our planet and how it moves across our planet, water is a very large vector for that. And we can see here, this is just an example of wind and temperature. This is a GIF from the website earth.nullschool.net. If you've never looked it up, it's a really, really cool site. I have the link down there in the bottom. But we can just kind of see we have an incredibly dynamic and diverse planet. We've got, we can see some mid-latitude cyclones spinning. We see the jet streams impact on surface winds. We see, potentially ocean current impacts as well. There's a lot of things going on in our oceans and in our atmosphere that drive energy and the budget of energy across our planet. We might remember back from a few lectures ago on looking at solar radiation. So we've got our sun. Total solar electromagnetic radiation is equal to about 3.83 times 10 to the 26th watts of energy. Then we have how much solar electromagnetic energy does Earth intercept. Radiant energy in is about 1.74 times 10 to the 17th watts, or averaged across our planet, 341 watts per meter squared. So what about energy out? Is it the same? Is it different? What do you think? Well, if we think back to some of our laws of thermodynamics that we talked about in previous videos, energy in equals energy out. It's the same thing. 1.74 times 10 to the 17th watts, or 341 watts per meter squared. These need to balance. If we think of this as a balance, we have to, or a budget, for example, which we'll talk about here, we have to think about how energy in and energy out balances one another. And we call this thermodynamic equilibrium. Like I said, we thought back to our laws of thermodynamics, particularly the first one, the law of conservation of energy. So here we're going to start building a budget. And I hope you're taking notes, build this along with me. So first off, we're going to assume that we have incoming solar radiation. We should, right? We always do. And here it is coming in at a rate of 1.74 times 10 to the 17th watts, as we said before, or 341 watts per meter squared. So let's actually simplify this a little bit, because that's kind of a nebulous number. So let's just assume that we have 100 units. So that impacts, or that comes into our atmosphere. So we can assume this is the top of our atmosphere, or quote unquote top of our atmosphere. So just by our atmosphere alone, gases, particles, whatnot, 23 units of that 100 units are reflected back to space. Another 23 are absorbed by the atmosphere. So water vapor, gases, particles, etc., absorb another 23% of that, or 23 units of that. Then that ray impacts the surface, and about 7 units are reflected back out into space, and 47 of them are absorbed by the surface of our planet. Now, what does our Earth emit? Well, it emits 116 units. Well, that doesn't match, right? We have 100 incoming and 116 outgoing. Well, that's not the only part of our budget here. So of that 116 units emitted, about 12 make it to space. Another 104 are absorbed by our atmosphere. So that's all of it. that's the rest of it, right? And those are absorbed by our greenhouse gases. Think of things like water vapor and carbon dioxide. So there are two primary atmospheric gases, that water vapor and carbon dioxide, that absorb a significant portion of that long-wave radiation emitted by Earth. As Earth's radiation heats these absorptive gases, the temperature of the atmosphere increases. In turn, the atmosphere radiates some of this energy out into space. More importantly, it radiates an equivalent amount back to the surface. So let's see what that looks like. So from our atmosphere emits another 156 units of energy. 58 of that radiates out to space. Another 98 is absorbed by the surface of our planet. This process here between the absorption by water, vapor, and carbon dioxide, and the radiation out of that back towards the Earth's surface, where it further warms the lower atmosphere, is what we call the greenhouse effect. So we've got other forms. We've got conduction, or sensible heat, the heat that we can basically feel, right? 5 of that is emitted, and 5 is absorbed by our atmosphere. We've got 24 units are emitted by evaporation in the form of latent heat, a phase change, right? To convection and condensation. 24 is absorbed by the clouds. So basically what we're saying here is that the conduction and evaporation through convection, what's emitted is reabsorbed within our atmosphere. So here's our budget, right? We've got this budget. Well, there are some misnomers here that we need to maybe clear up, and I would absolutely recommend looking at this website, Bad Greenhouse, and Bad Meteorology by Dr. Alistair Fraser. Really, really great kind of short piece on how we misinterpret these terms. I'm going to read out part of this page here. So from Dr. Fraser's page, however, without the greenhouse effect, Earth would be uninhabitable, as I mentioned previously. It is becoming increasingly clear that we're also experiencing global warming, but that is a different matter. The greenhouse effect is the name applied to the process which causes the surface of the Earth to be warmer than it would have been in the absence of an atmosphere. We have an atmosphere. We need an atmosphere to survive. So back to Dr. Fraser, global warming is the name given to an expected increase in the magnitude of the greenhouse effect, whereby the surface of the Earth will almost inevitably become hotter than it is now. The surface of the Earth is warmer than it would be in the absence of an atmosphere because it receives energy from two sources, the sun and the atmosphere. So we have to think that there is natural process going on here. The greenhouse effect isn't a bad thing. In fact, we need it to survive, but it's being exacerbated by anthropogenic activities. And in some of our future videos, we're going to dive into that a bit more on, if we've already thought about it a little bit. We think of the Keeling curve and carbon dioxide emissions, right? Or methane emissions. And we think of how that's changing, and maybe water vapor in the atmosphere, how that is impacting and warming our lower atmosphere at a rate that exceeds normal greenhouse effect and greenhouse gas emissions. So we are emitting and expounding upon this issue, even though in itself, the greenhouse effect isn't a problem. In fact, it's how we live on this planet. So the next question to ask, well, what would happen to this budget if the sun would be colder, if it wasn't emitting as much energy as it is? So just kind of think about that for a second, maybe pause the video and go ahead and continue it when you want. If the sun would be colder, this budget would pretty much be similar. Because of that thermodynamic equilibrium, what comes in has to go out. Although the temperatures on our planet would be colder, the atmosphere more or less would still be there based off of how our Earth has developed and evolved over the years. So if it was colder, this budget would be similar, but it would be lower, I guess, in unit than it is. And that 1.74 number that we mentioned previously, the watts coming in from the sun, would be lower. Likewise, if the sun was hotter, these numbers would be higher likely than they are in this version or this example. But what's in goes out, right? It has to. We need that equilibrium. What would happen if the planetary albedo increased? If we think back to our last video, we mentioned that word albedo, and that's basically how reflective a surface is. So higher albedo, higher reflectance, lower albedo, lower reflectance, more absorption. So if we had a much more reflective planet, we had a higher planetary albedo, what do we think would happen? Well, a lot more of the energy that's absorbed would be reflected back into the planet or back into outer space. So that 23 units that are reflected to space, or the 7 units that are reflected to space versus the 47 that are absorbed all the way over on the left-hand side there, a lot more would probably be getting absorbed into space because we have a much more reflective surface. And if you think of kind of specular reflection, like we talked about in the last video, we would have a better translation of energy being reflected from, a mirror-like surface. Likewise, if it decreased, if planetary albedo decreased, we would expect to see a warmer planet because more is being absorbed, more is also being emitted, but there's kind of a greater rate that's being absorbed into the planet, a kind of a better ratio, 1-to-1 that's being absorbed. And how is humanity affecting that global energy balance? Well, there's a lot of ways, and we're going to talk about some of them in future videos, but we are directly increasing the amount of greenhouse gases in our atmosphere. If we're doing that, we are leading to greater absorption and radiation from the atmosphere, so we're increasing the temperature in our lower atmosphere. So we're adding greenhouse gases, and we're enhancing that greenhouse effect. The result of that is anthropogenic global warming. We've talked about kind of how the climate has changed briefly in this class so far. We're really going to start to hit it as we go forward in these next videos. In the next video, we're going to have actually a number of NASA and NOAA developed videos that we'll watch within the lecture to kind of show those rates and show that change over time. But here we can see it. So here is our 20th century average. The 0 degrees C number is our 20th century average. And here we can see temperature anomalies from 1880 through 2022. So these are global land and ocean anomalies from January to December. And we can see right around the 1950s, there's a pretty severe pivot point. And we'll dive into what some of those drivers are in future videos, but there's also a link on the bottom to a NOAA Global Time Series page to show where this data actually came from, if you want to toy around with it and look for yourself. So when will the warming stop? Well, it's hard to say, right? I mean, if we went completely carbon neutral, the entire planet, we just cut out greenhouse gases or the addition of greenhouse gases, we would stabilize. But those gases without a source or without a potential sink are still there. And based on our rates of carbon, or of like things like deforestation, so we're removing our carbon sinks, and with stable carbon sequestration, maybe we would see a decrease in those greenhouse gases over time. And the greenhouse effect maybe as well would kind of stabilize. But there's a lot of changes that need to happen for that to take place. So what about global dimming? We heard this term before. So maybe if you took conservation of the environment with Dr. Doug Faulkner, or maybe Dr. Gary Running, or maybe you heard about it in 104. Well, global dimming is this idea that with kind of an increase in cloud cover, more water vapor in the atmosphere, because of greater temperatures and greater evaporation rates, maybe we could see some decreases based on the fact that there may be more cloud cover in the atmosphere. So I'd like you to learn for yourself what global dimming is. In fact, that will be our next random assignment. Dimming the sun, it will be on Canvas. So I want you to answer these questions, and this will also be on Canvas. But what is global dimming? What is the cause of global dimming according to research over the Indian Ocean by Ramanathan and colleagues? And then how much has global dimming countered the enhanced greenhouse effect in watts per meter squared? So go ahead and look for that video in our module. I will post it so it's ready for you all. And I hope you enjoyed. It's a really interesting video, a little bit older, I think around 2000, early 2000s, and when this one came out, but a really great video in general. So go ahead and watch that one, and I will see you all in the next video. All right.